Okay, welcome to period 4. We're going to do a one sample t-test for a mean example problem here. The students have already finished putting in all of these data values into a column in their calculator. Could someone read us the question here? Who wants to read us the question for this problem? Galilea, thank you so much for volunteering. Thank you.
Is there evidence that the machine is shortchanging us?
Can you read the whole paragraph?
Coffee machine dispenses coffee into paper cups. It's supposed to get 10 ounces of coffee, but the amount varies slightly from cup to cup. Here are the amounts measured in a random sample of cups. Is there evidence that the machine is shortchanging?
Do you guys have, thank you, do you guys have experience with this? Like maybe at your house, a Keurig or some other coffee machine, or maybe at your place of work, they have coffee machines that you put in, you hit a button and it dispenses? You've seen that before, right? You never seen that before? They have machines you put the little like cup in, hit the button, and it just brews it. It's pretty cool. It's pretty instant. Anyway, I'm not a coffee drinker, but I'm impressed by science. Anyway, so the reason I bring it up is, do you think it's the same every time? Do you think if you were to do it, like actually do this and measure how many ounces were in the cup, would it be the same? I don't know, right? I've never done that because that seems like a waste of 20, K-cups. I'm not going to buy that. That's expensive. So they've given us some data. They're saying, hey, we did it. Do you think, based on this data, that there's a problem here? That we should go to the manufacturer and say, hey, you're telling me I'm getting 10 ounces, but I'm not getting an average of 10 ounces when I do this. That's what we want to figure out. So let's define a parameter first. You guys remember that statement? Yes? Who wants to give it a shot? Anyone? What's it start with? Let P. Oh, Susanna, it hurts so much. Let T, not T. We are going to use T, not Y. We're getting closer, right? We're saying all the letters. No one? Let mu. Now you should do the symbol. I can't do the symbol. I mean, I can write the symbol. Let mu represent the what? Let mu represent the, what is it? Ounces. It is ounces, but if I say mu, what am I talking about? The average number of ounces. The average ounces in a cup of coffee. Oh my gosh. Sorry. Let's try again. Everybody good? Now, do we know what this is? Do we know what mu is equal to? Do I know exactly what mu is equal to? The answer is no. But what do I think it is? I think it's 10. Very good. So the null hypothesis is that mu equals 10. So I'm going into this test thinking that when I do this, I should get an average of 10 ounces. What's the alternative hypothesis? I know it's mu with 10, so we have options. What are our symbols that we could use here? What are the options we could use for the symbol? What, not equal to, I think I heard less than, or greater than. So what in this problem is telling me the symbol that I should use? I see short-changing. Short-changing. What does it mean to short-change someone? To be less than, to not give them enough. So that'd be less than. Questions? Now would be the time to ask questions if you're confused about defining the parameter and the hypotheses. You should see that this is the same step we did with proportions. But do you see any P's? No. So hopefully your brain sees that the process is the same, just using different symbols. What comes next? What comes next? The assumptions and the conditions. So the first assumption is actually no different than what we did with proportions. That's the independence assumption. Who wants to give that a try? Who wants to give that statement about independence a try? Anyone? Okay, Susanna.
One cup of coffee won't be.
Ooh, do you want to say won't be the same? Could they be the same? They could, right? I want to say it won't affect. And really, what about the cup of coffee? The ounces. So I would actually say 1 coffee cup's ounces won't affect another cup's ounces. Something about ounces I need to see in there. 1 cup's ounces, right? If you brew a cup and you get a number of ounces, then you brew another cup, it will not be related to the one you just brewed. That's what you're looking for here. Now, how do you guys feel about that? Do we feel like we're going to be okay and we can assume that and feel good about it? Any thoughts? Are you worried about it? I mean, I don't have much experience with this, but you just fill up like a little water part and then you hit the brew button. So it's really, if the same person is doing it, I can only imagine it'd be no issue, but I don't know. I have no idea. So what do we check to make us feel a little bit better about it? We check the randomization condition. What's the other one we check? The 10%. Now the 10% condition, we're going to check it, but it's not nearly as important as it was to check when we had proportions. All right, so I'm going to keep writing it and keep checking it, but I want you to know that with means, when you're doing a t-test for a mean, it's not as important as it was before, but we're still going to put it. All right, does it say anything on the problem about randomization, about randomly sampling? Random sample 20 cups. Okay, there you go. What math am I going to do for the 10% condition? I'm going to do n times 10. Well, what is our sample size? 20, so that would be equal to 200. Do we think there are more than 200 cups brewed by this machine? Probably. Whether it's a personal machine or a machine at the office or a machine at Jiffy Lube, it's going to be over 200. So everybody good on that one? That's really no different. I'm hoping we feel pretty confident about that. There's no difference with what we did here with means and with proportions. The independence assumption, all these conditions are the same. What's the new assumption? What's the new assumption this week? Not the nearly normal. What's the new assumption? The normal population assumption. This one is a little tricky. Basically here, we're saying that we think if I had the number of ounces for every single cup that this machine brews, and I looked at a histogram of those numbers, what would it look like? It would look unimodal, so one hump, and roughly symmetric. Now, do I know that? Do I have that data? Can I make that histogram? The answer is no. And guys, most of the time the answer will be no. You won't know. All right? So we just assume it is. We assume it to be true that the population that this sample comes from is unimodal and roughly symmetric. But since I don't really feel great about that because I have no data or no histogram to look at, I check a condition called the nearly normal condition. Now I'm going to do this condition for you up here on the board so we can decide if we think we can move on. So you guys already put all of your data values in your calculator. My calculator is a little bit better than yours. So I'm going to make a histogram. Do you remember what this is called? Oh, just for fun. Somebody said it. What is it? Somebody said it? A dot plot. Nice job, Juliana. Well done. Now, do you see I have gaps in my bins? You see I have gaps here? I don't want gaps. I'm going to change that real quick. Okay. What do you think? What do you think about this histogram? What do you think? We're looking for it to be roughly symmetric and unimodal. Is there any big gaps? Is there any really long tail going in either direction for some skewness? Or do you think, hey, I have no reason to believe it's not unimodal and roughly symmetric? What do you think? No thoughts? This looks unimodal and roughly symmetric to me. I don't see any skewness or any gaps. There's no two humps, right? It's not bimodal. So when I do this, I'm sketching this on the nearly normal condition. So right now, on your notes, do you guys have an area where you could sketch the histogram underneath? Doesn't need to be big. It can be a small histogram. Can you go ahead and sketch this histogram? Go ahead and sketch this. Can I save this? Yes, I can. Excellent. All right, so after you sketch this, we are ready for our statement. Sketch it. I should have made myself clear when I said sketch it. I wanted to see the actual bars. Yes? Let me show you. I'm imagining on your paper you have the bars. Yes? Okay. I don't mean sketch like a curve. I mean the actual bars, the histogram. There you go. Perfect. Thanks, Demo. Okay, start thinking about the sentence we're going to write. Think about what we wrote for proportions. We've just made our assumptions. We've checked our conditions. So what is the statement we're going to write? The conditions have been satisfied. That's the first part of it. You want to keep going, you said? I'm sorry? Yes, Andrea? No, you can say what's up. I can go back. No, you're good? The conditions have been satisfied. So what? So I will not be careful. I will now use, be careful here, be careful. T. Ooh, the T model. With, I think I heard Adriana say it, how many degrees of freedom? 19 degrees of freedom. Say it again. This statement is basically telling the person reading it what you're going to do. So you're saying, I'm going to use a T model with this many degrees of freedom to run a one sample t-test.
You can put for the mean?
You can. For the mean is fine. Do I need to go back to the histogram? Anyone? No, we got that sketch. Okay. Okay, now we're ready to transition to what part of the test? The mechanics. And guys, this is what most students think is like the math. So I want you to go back to your calculator. So turn your calculator on. It's probably gone off now. So turn your calculator back on. You should have everything in one of your lists, all 20. And I want you to go, do you see where you click data, but there's like a green word above it that says stack? Hit second data so we can do that. Second data, and then you should have something that says one variable statistics, one bar stats. Okay, hit that. Do you see how yours should be flashing on L1? Is yours flashing on L1 now? Yes? See what it says frequency, FRQ, frequency, leave that alone. Second data, enter, enter, and you just got to hit count. Now if you have, calculate. If you have your list not in L1, then where it says data, you need to go hit enter on whatever list you have in L2 or L3. All right, and then if you take a look at your calculator, what is this giving you? It's giving you n. What's n? 20. What is that though? The sample size. What about x bar? We're not going to use x bar. What do we use? We use y bar. That is the, I think I heard somebody say the sample mean. Then you have SX. Do you guys see SX? What is that? What's sample? What's S? What is S? The sample standard deviation. We're going to use that. You're going to write that down. All right. Everything else is we don't need. But you should see some things you've seen before, like the quartiles and the median. All right. So let's write down some things. Let's write down our sample size, our degrees of freedom, our sample mean, and sample standard deviation. So that's going to look like this. So we have n equals 20. What's our degrees of freedom? 19. What is our y bar? 9.845. And that's in ounces. And then our S, or sample standard deviation, is, I'm just going to round here, 0.199. Any questions on where we got these numbers? Okay, so now we're ready to find our t value. And when I write this, this is where I would have written the z, all right, but with a t distribution, when I find my t-score or t-value, I need to put a little subscript for the degrees of freedom. So that's going to be a little baby 19. All right, so always make sure that you're putting the degrees of freedom. The formula is going to be y bar minus mu over the standard error of y bar. All right, what's y bar? 9.845. What is mu? What did we say mu was equal to in our null hypothesis? What do we think the average is? 10. You notice our sample average, our sample mean was below it. Over, do you guys remember this formula? This is where you have the sample standard deviation over the square root of the sample size, which is 20. All right, now you can type all that in your calculator if you'd like. What I'm going to do is I'm going to move to the internet where there's a link where we can actually do this, and it gives us all this information. All right, so I'm going to do that right now. And if I ask you to do this, obviously you'll be given this link. All right. Okay. Thank you for your patience. Here we go. Come on, internet. There it goes. All right. This should look familiar. Math cracker. And what is our sign that we use for the null hypothesis? No, null hypothesis equal to the alternative hypothesis less than. What did we say mu was equal to? 10. What's our sample mean? This is y bar. 9.8. Very good. Our sample standard deviation. What's our sample size? And what alpha would you like to use? 5? 0.05. Excellent. All right. Don't click on the add. Hit solve. Yay. Okay. Should see a bunch of stuff here. The first thing I want you to write down is the test statistic. You guys see the test statistic? You should see that the work just like our work. So let's write down that number. Looks like it's negative 3.483. Negative 3.483. Now, you guys have a blank slide after it, right? Flip it over for me, Galileus. Do you have more slides over there? Excellent, even more slides. Yes, go to the next one, like the next slide on that same page, and I want you to draw a curve. Yes. Say it again. That's what we're about to draw right here. All right. Negative 3 point whatever that was is going to be really far to the left. Was it 483? Yeah. And which way am I shading? Less than. So which direction? To the left. Now, do you remember what this is called in here? What is that called in there? I think I heard Yesenia say it up here. It's called the p-value. All right, let's go back to the internet. What is the p-value? P-value is, you see it here, the p-value is p equals 0.0012. So 0.0012. 0.0012. Ah! Thanks, Peter. Okay. Now, immediately when I read that p-value, what's my brain know about that p-value? Greater than 0.05? It's positive, but all p-values are positive. That's alpha, right? That's way less, right? 0.0012 is way below. That's basically 0, right? 0.001 is 0.1%. That's tiny, guys. 0.1% is very unlikely to happen. So if we think that it's really unlikely to have gotten this sample, given that we assumed 10 was the average, what's more likely to be happening here? What's more likely to be happening? What should we think about our hypotheses? What should we think about our hypotheses? It's less than 10. We need to go back to the manufacturer and say, hey, you are lying. We just ran a test and we found significant evidence that the average number of ounces in our cups is less than 10 ounces. I don't know what it is, but it sure isn't 10. Give me my money back. Okay? So let's write a conclusion. So flip your paper to the conclusion page. Yeah. All right. I don't know why I did that. That's not what I want. There we go. Okay. What do you want to say? Who wants to give us a sentence here? Conclusion. Something about what? What do I need to put in the conclusion? Even before that, I want to mention something. What did I calculate? I calculated a p-value, right? The p-value is below my what? My significance level, or you can put alpha. significance level. That's alpha. There is enough evidence to do what? To reject the null hypothesis. Now, this is all good, right? But where do we struggle in this class? What has not happened yet in this conclusion? Context. And this is where you guys, for the test, you'll go to the website and you'll write down the conclusion, right? See, take a look here, this conclusion. And if you read that conclusion, is there any context in there? There's zero context, which is why I have to take out points. So give me some context. Who wants to try some context? There is enough evidence to reject the null hypothesis. What am I saying? I believe that the amount, the average amount of coffee dispensed is what? Less than 10 ounces. I'm going to pause here. Please ask if you have questions right now. I hope as you're writing this down, you recognize this is new material, but you also recognize so many similarities to what we've done with proportions. The whole setup of parameter, hypotheses, assumptions and conditions, do the mechanics, make a conclusion. I mean, guys, it's all the same basically. For type 1 and type 2, that will always exist. Right here, we just rejected the null, so there's a chance that we've done what? Committed what? A type 1 error. Rejecting the null and being wrong would be a type 1 error. Do I know if I've made a mistake? No, what I could do is do another sample of 20 cups, run the test. Another sample, 20 cups. Maybe do a sample of 1,000 cups. Take a larger sample, be more confident. All right? Now, I'm going to pause here for the day, but where am I going to go to next? Well, we're going to start with tomorrow morning. I guess I see you in the afternoon. Tomorrow afternoon. We're going to start tomorrow afternoon. We just told everyone reading this, listening, that we don't think it's 10 ounces. So what's the next question? If I don't think it's 10, I think it's less than 10, and the question is, what is it? If I don't know what it is, then what do I run to tell me what I think it is? What do I run? What? We just ran the test. Now what do I run to tell myself, hey, it's less than 10, here's what I think it is. Not trying to trick you here. We just did the hypothesis test. Now we're going to run a confidence interval. The confidence interval will tell us where we believe the average is. Okay? All right. This is Mr. Vrander for period 4, signing off. Have a wonderful day.